In this video, we're going to start the graphing section. So to be able to graph a function using calculus, we need to first start by talking about the extreme values. The extreme values are extremely important to us when we graph because they're the key points that we find to begin with, and then we connect the points using other calculus information. So to start off, we're going to talk about the absolute min and the absolute max of a function. So to do this, we need a theorem. It's called the extreme value theorem. And we're going to read this and then we're going to look at some examples to help us understand what this mathematical notation is trying to tell us. So if f is continuous, what does continuous mean? You can trace the whole curve without picking up your pencil. On a closed interval from a to b. So that closed means the endpoints are included. So you have solid dots at the beginning and at the end. So if f is continuous on a closed interval, then f attains both an absolute max, we'll call it capital M, and an absolute min value, little m, in that closed interval. That is, so this is clarifying what we just said. There are numbers x1 and x2 in our interval where f of x1 achieves the smallest value and f of x2 achieves the highest value of the function. And the function everywhere else for all other x's is in between the smallest and the largest value. So here's some pictures for us. So these are all the same parabola, but we're defining the domains differently for each picture. So first of all, a parabola in general. Does a parabola in general have an absolute max or an absolute min, or both or neither? All right, so to begin with, the extreme value theorem says if f is continuous. Now, a parabola is continuous, so we're good so far. On a closed interval, well, a parabola in general has actually an open interval. It goes from negative infinity to positive infinity. So the extreme value theorem would not apply in a general parabola situation. However, we can still talk about the absolute max and absolute min in terms of using the picture here. So if we look at this parabola, remember, a parabola continues up to the left forever and up to the right forever. So because it continues up and up and up, is there ever a maximum value that a parabola achieves? The answer to that would be no, because there's always a bigger value. So there is no absolute max in a parabola, or at least in this parabola. On the other hand, is there an absolute min? Well, an absolute min, by definition, is the smallest function value that the function achieves. So in this case, the lowest point is our absolute min. Now be careful, the absolute min happens at x equals 0, and it also has the min value of the function value at 0, which is 0. So this is a point x comma y, and that point is 0, 0. So the x value is where our min is, and the y value is what the minimum value it actually achieves, okay? So just because you're not on a closed interval doesn't mean you can't talk about an absolute max and absolute min, but the extreme value theorem wouldn't apply in that case to be able to help us say for sure that there's a max and a min. All right, so let's go down to number 2 down here. So we have the parabola, but notice we've limited our domain. This domain has brackets on the 0 and the 2. So this is a closed interval. So we have a continuous curve, a parabola. We have a closed interval. So the extreme value theorem would apply here. What does that mean? That simply means there is a absolute max and an absolute min in the interval from 0 to 2. Now, if you look at our picture, we can actually see where they are. Pictures are nice. We won't always have pictures, but I'm starting off with pictures to help you understand what we're looking for. So we can only consider from 0 to 2, those x values. Anything outside of that doesn't exist because our domain is restricted. So we're looking for an absolute max and absolute min. In this case, you can see that the absolute min is achieved at 0. This is the smallest function value, which is a function value of 0. Remember, this is at 0, 0. The x value is the location, the y value is the minimum. So the y value of 0 is our absolute min. At the other end of our interval is the highest point that we achieve. So this is our absolute max. In this case, the absolute max is equal to, well, we just plug in x, so 2 squared is 4. So the absolute max that we achieve is 4. So the extreme value theorem applied, it told us that there was a max, absolute max, there was an absolute min, and we were able to look at the graph and see what they were. All right, let's go over here and see what happens if we don't have a completely closed interval. So what if we have an open interval? So we do not include the 0 on one side, but on the other side we are closed. How does this affect the results of the intermediate value theorem? Well, obviously the intermediate value theorem doesn't apply, but why? Well, we still have our absolute max. That does not change. But then again, that's where our closed bracket is. We include that endpoint. The problem is this other one right here. There is no absolute min. But why? Well, it's an open circle. So what used to be our absolute minimum value is no longer absolute minimum value because it doesn't exist anymore. So why is there still no other point that's our absolute minimum? Okay, so remember, the open circle is at 0. When we follow our curve towards that open circle, we can get closer and closer and closer and closer and closer to it. You can always get closer to that point, which means there's always going to be a number closer to 0 than your previous one. How close to 0 can you get? Infinitesimally small. Meaning, no matter how close you get to that open circle, there will always be a closer value, which means a smaller function value, which means a smaller value, implying that you still have not achieved your minimum value possible. You can always go smaller. If you can't achieve the absolute minimum value, can't find the smallest possible, then there is no absolute min. So that's a little bit to help you with that. Down here we have, now both sides are open. This is a completely open interval. So again, the extreme value theorem does not apply. And the reason is you can always get closer to what used to be our minimum value, and you can always get closer to what used to be our maximum value. How close can you get to 4? Really close. You can always get closer. Excuse me. So, in this case, is there an absolute max? No, no absolute max, because you can always get closer to 4, meaning always get bigger. And there's no absolute min, because you can always get closer to 0, meaning you can always get smaller. So those are some examples for you of one where the extreme value theorem applies, one where we have no constraints on our domain, and then where we have open circles and how those affect having an absolute max or absolute min. Okay, so here's an example. Determine the absolute max and min for the function e to the x. Now, I've actually drawn the graph here. So we can look at the graph, but remember some things that we've talked about are continuity. You need continuity to be able to talk about absolute max and absolute min, especially if you want to get to the extreme value theorem. So in order for the extreme value theorem to apply, you need to ask these two questions. Is f continuous? Yes, absolutely. So far so good. Is the domain a closed interval? Well, what's the domain of this function? Well, if you look at the graph, you can actually see, and if you've studied e to the x in a pre-calc class, you should recall hopefully, you can plug in any value of x you want. So the domain is from negative infinity to positive infinity. So is the domain a closed interval? No. Does the extreme value apply? Well, we have a yes to continuous, but a no to closed interval, so no. But remember, that doesn't imply that there's no absolute max or absolute min. You still need to consider the function. The extreme value theorem really just says, I guarantee an absolute max, I guarantee an absolute min. It doesn't say that there can't be one. Now, in this case, if you look at the picture, you can see that this function goes up forever and ever and ever. What does that mean about a maximum? Well, no matter what, you can always go bigger, so there's no absolute max. On the other hand, this curve continues to go down, down, down. What's it approaching? Well, maybe some of you remember. E to the x approaches this horizontal asymptote at y equals 0. It keeps getting closer and closer and closer to 0. which means it's always getting a tiny bit smaller, smaller and smaller and smaller. It never actually reaches zero though. If it reaches zero, there's your min. But because it's a horizontal asymptote, you get closer and closer and closer, but you never actually reach it. So if you can always get closer to zero, that means you can always have a smaller value for your function forever and ever and ever, but you can never reach the smallest value. So because you're approaching a horizontal asymptote, there is no absolute min for this function. All right, so extreme value theorem is awesome because it can guarantee something, but if it doesn't apply, you still have to look at your function and analyze it on its own to determine if it has absolute max or min. So those are absolute max and min. We also have things called local or relative min and max. So absolute extreme values are important, but there are cases when we want to consider locally extreme values. So we call it a neighborhood. If we look at a particular x value and just the values around it, is that x value a max or a min within a small area? Think of yourself as having binoculars and zooming in on your curve. So if I were to take my binoculars and zoom in right here, you can see that this particular point is a maximum in that little area. If I zoom out with a big circle, then obviously there are points higher than that one over here. This guy's higher. But what we're interested in is just, whoops, around that particular x value. Is there anybody bigger or smaller, or is that the maximum for that area, or is that the minimum for that area? All right, so for a local max at x equals c, this would occur, a local max, when all the neighboring points, the nearby points, are below your function value. So at c here, you can see we have our point, and all the neighboring points, just in a small region around, are all lower than that. So that is a local max. It's not the absolute max, like I said, because this guy over here exists, which is higher. For local min, same basic concept. Let's look at E. So x equals E. This is a local min because all the points around it, in a small interval around, are all higher than your point. Okay, they're all above f of E. Now, we can talk about absolute min and absolute max. You would have to find all your local extrema and figure out which one has the absolute maximum value and absolute minimum value. Notice here, we can talk about local min being at the endpoints. Can also happen. So be cautious of the endpoints. Sometimes those are a little bit harder to see. Notice here we have this weird looking shape. Okay. Generally, most of the time, we're going to look at nice smooth polynomial curves. So we're going to look at the local min and the valleys and local max at the peaks. But sometimes we're going to have weird cusps in our curves, and you're going to have to be careful of how to find those. All right, so I think I talked about everything here. Oh, I know. These little red bars on these two here, this local min and max, what are those representing? Hopefully you're saying tangent lines. So this red bar here is the tangent line at C, and this one here is the tangent line at x equals E. What do you notice about the tangent lines at this local max and local min? You should be saying the slope of these particular tangent lines is 0. These are horizontal tangent lines. We've talked about horizontal tangent lines before. But horizontal tangent lines are going to be very useful to us because they occur at many points where we have a local min and a local max. And we're going to talk about that in the next video when we start finding these. So we've looked at the visual. Hopefully that helps you out a little bit in terms of understanding what we're trying to find, but in the next video we're actually going to learn how to find the local min, local max, absolute min, absolute max, and all that good stuff. So study hard. I'll see you in the next video.